So let me recall you where we were in 2 days ago. So X is a regular projective flat scheme of Z. And L bar is an Hermitian line model on X. So we stated the following theorem. There's a unique way to attach to every closed irreducible y in X, subvariety of X, a real number H bar of Y in such a way that first, if the dimension of Y is 0, that is Y is a closed point, then the height of Y is log of the cardinality of the residue field. Second, if dimension of Y is positive and S is a section, S is a rational section of L on Y, with divisor the sum of n alpha y alpha, then the height of Y is the same as the sum n alpha HL bar of Y alpha, and the correction term minus log integral on YC and complex point of Y of log norm S C1 of L bar to the dimension of YC. So we define the height by induction. First, when the Y has dimension 0, this is just log of the cardinality of the residue field. And when we know it in degree d minus 1, then we know it in degree d by this formula. I mean, Y alpha is the divisor on Y, so it's one dimension less than the dimension of Y. So by induction, we get the dimension, we get the height for any Y. So let's start discussing the fact that the height defined this way is independent of choices. But let's just give first an example. Assume K is a number field. Let X be the spectrum of the integers in K. Let sigma the set of embedding of k in complex numbers. Then the set of points of x in C is simply spec C to the power sigma, when there is a point for every embedding. To give L bar on X is the same as to give rank 1 projective OK module lambda together with norms. So for any sigma, in sigma we have a norm on lambda tensor C. And we ask that it's invariant by the conjugation. So if we have X and we apply F infinity, the conjugation of F, of X, the norm for this complex embedding is the same as the norm of X with the complex embedding sigma. Okay? Now, what is the height of X? Well, if S lies in lambda, S non-zero, the divisor of S is the sum of all close points, so all prime ideals of K. And the height of X by the second axiom will be the sum of a P of n beta np log of the residue field, so log of np, where np is the cardinal of the residue field. So this is the first term in the formula here. And the second is the integral is just integral on points. So we get sum for all sigma and S in sigma log norm of sigma X norm sigma. Okay? What? Why is it so? Because the integral is on YC, which is the divisor Y. What do I want to say now? The set of points of X is the disjoint union of points. So the integral will be evaluation of the points of XC. So we have the dimension of YC is 0, so this term is 1, and we get log of norm of S evaluated at all these points. So sigma I wrote it somewhere already, sigma is precisely the set of complex points of X. So if we evaluate log sigma, or maybe I should write S instead of sigma. So if we evaluate log of norm S at a point given by some complex embedding, this means that we look at the norm of S at this place sigma. And we get the sum of all this because we have to integrate on the whole of X of C. Is it okay? So this can be written in different way. Lambda divided by OS is a product over all prime P of OP divided by P NP, where NP is the valuation of S. So the first term, sum of over all P of NP log NP, can be written also as log of the cardinality of lambda divided by OS because of this equality here. Okay. So the statement is that this norm is that this height does not depend on choices. We have chosen S, but the height will not depend on S. Lemma, mass 6, is that HL bar of X does not depend on the choice of S. Indeed, this means the following: let ds be the log of the cardinality of O divided of lambda divided by OS minus sum over all sigma log norm of S to the sigma. So maybe sigma of S. So we have to show that ds doesn't change if we change the section. So assume you have another section. Then you can write S prime equals Fs, where F is an invertible element in K, because the rank of lambda is 1. So if we compute ds prime, we get essentially ds, but there is a correction, namely the sum for all p of Vp of f log np, that's the finite place contribution, minus the sum of all sigma and sigma log sigma of S sigma. Right? This term varies according to valuation of F, and this term varies according to the absolute value of sigma of F. Okay? Now this difference is 0 by the product formula. if I have f an element in K which is non-zero, the product over all prime P of f to the power of fp times the product over all sigma this product is equal to 1 by the product formula. If I take the logarithm, I will get that this difference here vanishes. So maybe there is a minus here. Okay. So the product formula for number field implies that the height is well defined in this case. So let's look at a more complicated example. Well, first I would like to give an exercise, which I was trying to do when preparing the talk, but I did not finish. So X is Pn over Z, and P is a point in Pn. Then we can choose the coordinate of P to be integers prime to each other, no common divisor. On Pn complex numbers, we have the line model O of 1 with a standard metric. O of 1 is a quotient line model on the projective space. So let L bar be O of 1. Consider H L bar of Y. I mean, we can think of this point P as giving a map from spec Z to P and Z. And let Y be the image of U. Then the height of Y, which is like the height of the point, if you prefer, is exactly 1/2 log x0 square plus xn square. So the height of a point in the projective space is the height, I mean the so-called naive height of a point in projective space. So this is exactly the formula that Gendron was giving for the height of a point in projective space. Okay? Now consider a case which is a little more complicated. Consider Y in X of dimension and we ask that I is the horizontal, by which we mean that the image of Y is space Z. We have X mapping by F to spec Z. And we ask that Y surjects on the base. Dimension 1, but horizontal. Well, then the situation is as follows. If we think of the generic fiber, so we look at 0 if you wish here, and we have the generic fiber x q. Well, this line will give a point to the generic fiber, call it small y, and this is the generic point of y. Y is the closure, the hierarchical closure of the singleton with y this point. Okay. This point, small y, is a finite extension of Q. The residual field is a finite extension of Q. So we have a number field, K, which is the residual field of the scheme at Y. And Y is now an affine scheme, spec of R, where K is a fraction field of R. But the scheme Y need not be regular. In fact, it doesn't need to be integrally closed. So we let R tilde be the integral closure of R in K. So now we have an integrally closed subring of a number field with fraction field K. So R tilde is simply abstractly the integers in K. So if you wish, you have spec OK, which maps to Y and resolves the singularities. Okay? So we have a projection from Y tilde called spec of R tilde onto Y. Okay. Now assume I have a section of L on Y. I can consider the inverse image of this section to get a section on Y tilde of pi alpha star of L. So we shall prove the following. D of S is the same as D of P tilde S. That is to compute the height of Y. We need a section of Y. So we get D of S by definition. And what this equality will mean is that the height of Y is the same as the height of Y tilde. We proceed as follows. Well, first, you have the complex planes, but the complex planes are not difficult to deal with because Y and Y tilde have the same set of complex points. So part of D of S log absolute value sigma s sigma is the same as the sum of the same expression for S tilde. So there is nothing to check at infinity, but R and R tilde might differ at finite places. So we have a commutative diagram. Which is the following. So for instance, R goes to L over R, L over, so by the section S. We have the same thing with R tilde. R tilde go by S tilde to L tilde with quotient R tilde S tilde. So I should I keep R. Okay. So then there is a map from R to R tilde, from L to L tilde. And the quotient are R tilde over R. I want to keep R tilde here. R tilde over R, L tilde over L, and now I have some zeros. But here, for instance, I have a non-zero kernel, call it big K. Here I have a non-trivial co-kernel, K prime. Here I have a kernel. Let's call it K prime and this one K double prime. Okay, that's the diagram we get from the picture of S and S tilde. We are interested in the quotient of L by RS, because this is what counts in defining ds. And we have the diagram here. Okay. So S tilde is the inverse image of S, and L tilde is the inverse image of L. So when we have a diagram like this, we can chase in the diagram. Namely, we can start from a point in K, look at this image here. This image here is the quotient of an element in L. You look at the image of this element in L in L tilde. The image will be 0, so you can lift it to R tilde and look at its image in R tilde R, and you will be in the kernel K prime. So there is a map from K to K prime. And it is easy to show that it's an isomorphism. So the diagram implies that K is isomorphic to K prime. Okay. On the other hand, for any prime ideal in R. The quotient L tilde divided by L localized at P. Well, locally L tilde is the same as R tilde, and L is the same as R. So at least the cardinality is the same for L tilde over L and R tilde over R. This is because L tilde is locally free and L is locally free. Okay? So this quotient R tilde over R is the same as the quotient L tilde over L at every prime. So the cardinality of the kernel is equal to the cardinality of the co-kernel, because in the middle, at each prime, I have an isomorphism. So the cardinality prime is the cardinality of K double prime. K double prime here is the same as K. Okay? So I claim now, so the cardinality of K here is equal to the cardinality of K double prime. Now look at this last vertical. The kernel and the co-kernel have the same order, so the two groups in the middle should be equal. At least their cardinality should be the same. So L over Rs has the same, L over Rs here has the same cardinality as L tilde divided by R tilde S tilde. Well, remember that dl whose log cardinality of L over Rs minus the sum sigma in sigma of whatever. We have shown that this part here is the same for S and S tilde. And now we just check that this quotient L over Rs has the same cardinality as this quotient for S tilde. So we conclude that ds is equal to ds tilde, which was the assertion made here. So in that case, you want to compute the height, you can really go to the normalization of the ring. Okay. Say it again.
So the bottom line on the left side of that
You ask for this equality?
Yes.
This equality is true because L tilde and L are locally free. So locally, L tilde is like R tilde and L is like R. Okay. So if we change S, we change pi F star of S, but we know already from the case of the number field that D of pi star of S is independent on the choice of S. So if we change S here, we get the same answer. So ds is equal to ds prime for any other section S prime of L. So we have reduced the case of horizontal dimension 1 scheme to the case of a number field. Now look at the following case, namely dimension of y is 1, y is vertical. Y is vertical means that y maps to a point. So y is a curve on a finite field. Then we can consider a resolution of this curve. And we apply the same argument we applied for the horizontal case by the same argument. We have to consider the case where the curve is smooth. But when the curve is smooth, we have a replacement for the product formula. So product formula is the number field case. By the formula sum over all x in y tilde of v of x of f. So f is a function in y tilde and y tilde. The sum of v of x f times the degree of this extension over the ground field is equal to 0. This is a reciprocity, maybe Veil reciprocity formula, that this sum is equal to 0. So if we replace, if we want to count, we say that sum of Vxf log cardinality of kx is equal to 0, because log cardinality of kx is just kx over k times log of cardinality of k. So we have this formula, which is the exact analog for vertical one-dimensional subscheme of the product formula for number field. So I will not give more details in the case of vertical dimension 1, which is treated the same way as horizontal dimension 1. Okay. So we have shown that this expression does not depend on choices when the dimension of y equals 1. So assume now that the dimension of y is 2. It's at least 2. So we consider y in x, integral subscheme So y is a closure of this generic point small y, and we consider a section, a generic section of L on y. So the divisor of S can be written some and alpha y alpha. Well, the first lemma lemma 7, we can choose the section. We can choose a section in a generic section in L at y in such a way that T restricted to y alpha is non-zero. We have finite sum of divisors, and we choose another section which is such that its restriction to y alpha is non-zero. So we have to show that there exists such a section T. Okay, so y alpha is again the Zariski closure of its generic point, and we can consider the following ring: the limit of O of U, where U runs to open subset such that there exists alpha such that y alpha is in U. So we consider open neighborhood. We have finitely many points, the y alpha, and we consider functions in the neighborhood of these points, of some of these points. So the ring R is not a local ring, it's a semi-local ring. That is, it has finitely many maximal ideals. We write I, so there are finitely many maximal ideal, which are written ML alpha because there is one for every alpha. So alpha here, alpha will run over a finite set big A, and for any alpha in A, we have a maximal ideal M alpha, which are given by functions which are 0 exactly at y alpha. Here, functions are 0 in one of the y alpha, so it's not quite the same. So, we call I the intersection of all maximal ideals. This is sometimes called the radical of A, or radical of R. Okay. Then there is a line bundle on on R, which is lambda equals the inductive limit for every alpha in A, alpha that same way we consider the localized line model at a point, we can consider the semi-localization of L. Now I claim two things. The first one is that R M alpha is the same as the local ring OY alpha, because R is semi-local and there is no choice of the alpha, but when we decide of which alpha are functions which are close to this point, we get the localization of O. And second, if alpha is different from beta, M alpha plus M beta is equal to R. Well, this is simply the fact that M alpha is maximal. So if I add anything to M alpha, I will get an ideal equals to R by maximality. Okay. Now let's consider lambda tensor R over I. We can decompose this according to the alpha as lambda localized at alpha, so OY alpha by the first property here, divided by M alpha. I is the intersection of all M alphas. So looking at this quotient is the same as looking at the quotient lambda tensor OY alpha M alpha at every point, at every index. Now this is the same as O Y alpha divided by M alpha, because lambda is L is locally free. And this is nothing but R divided by I. This is a Chinese remainder theorem for the intersection of M alpha here. R over this intersection is the same as the product of the quotients. Okay? So this means that if I call M the module lambda, I have to choose my section T now. Remember, we look for a section T which will not vanish at every Y alpha. So we have lambda tensor R over I is the same as R over I. In lambda, such that its image here maps to 1 in R over I. So here I have T tensor 1, and it maps to 1 in R over I. So now we can consider the quotient M, which is R, which is lambda divided by some module spanned by T. What we have shown here is that if I divide by I will get the same as a trivial ring. So I know that M divided by IM is equal to 0. That is, if I T goes to 1, goes to 1, so IM is the same as lambda divided IM is the same as lambda I divided by RI T, and now T is equal to 1, so it should be 0. T times 1 goes to 1. So if I divide out by T, it's like dividing out R over I by 1. So I get 0. So M over IM is equal to 0 because T goes to 1 in R over I. Okay, now there is a so-called Nakayama's lemma. I is the radical of the ring R. And I have M equals IM. For any module such that M equals IM, where I is the radical, M must be 0. This is Nakayama's lemma. So we get M equals 0, so we get lambda equals RT. Which means, so equal what was lambda. Lambda were functions around the points U, and we know that T goes to that lambda is spanned by T over R. So this means that T does not vanish on Y alpha. Okay, so that's the result. There exists a section of L at the point Y of dimension 2, such that at every alpha, T is not 0. So now we can keep on going by the induction hypothesis and look at the height by looking at the divisor of T on Y alpha. Say it again.
To prove the lemma, do you need to use a dimension of y is bigger than or equal to 2?
If you have dimension 1, you will not have room to. So let's call y of dimension of dimension at least 2. I mean, this lemma can only be true with when y has dimension 1, because you would not have room to choose t. We want to know that there exists a section which is not zero at y alpha. And if the divisor of S was a bunch of divisors, we would like to know that there exists a section which is non-zero everywhere. Maybe you're right. Maybe I could go on with dimension 1. We shall use it in dimension 2, but maybe the lemma as such is true when dimension of y is 1. So I will let you think about it and we'll discuss tomorrow. Okay. So we have that the divisor of S is the sum of n alpha y alpha, and we have this section T which does not vanish on any of the y alpha. So we can consider the divisor of T. It will be sum m beta z beta, and clearly y alpha is different from z beta because otherwise, if z beta was y alpha, we would have that t is 0 on z beta, therefore on y alpha. So by the fact that t does not vanish at y alpha, I deduce that the two divisors here are transverse in the sense that they are not made of the same divisor, of the same component. Okay. So we're interested in applying the second part of the definition to T. So we define the divisor of S point divisor of T to be the sum n alpha divisor of T restricted to y alpha. Similarly, we define the divisor of T times divisor of S to be the sum of all beta of m beta divisor of S restricted to z beta. So these are cycles of codimension 2 because y alpha is codimension 1, and then I take a divisor, so I get codimension 2. So we shall have the following proposition. these two divisors are the same. These two cycles are the same. Divisor of S times divisor of T is the same as divisor of T point divisor of S. So I will prove it probably tomorrow. Next, we have ds, remember, which was the height with respect to L bar of the divisor of S minus the integral on yc of log norm S C1 L bar to the d, so the dimension of y. And we want to show that this difference is dependent on the choice of S. So we assume by induction that we have defined the height of cycle in dimension 1 more. Assume the height is defined in dimension 1 less. Then you know what is the dimension of the divisor. So we have by the property 2 applied in dimension 1 less, we have that this is the same as the sum over alpha and alpha h bar divide the height of the divisor of t on y alpha. Here I mean an expansion of, I define the height for irreducible cycle. Here I use it, the same notation for arbitrary cycle by linearity. So this is the height of the sum of m beta, z beta, and this is the answer I get for this height by assumption, by induction. Okay, this is one thing, minus sum of n alpha integral on y alpha c log t C1 of L bar to the dimension of yc minus 1. So this term here is the right-hand side of the property 2 applied to divisor of S. I get this side and this correction term. But I still have the integral I was starting with, minus integral on yc log norm S C1 L bar D. So this is the same. We can write it as follows. This will be the height of div S div T minus some integral IST equals over all alpha n alpha integral on y alpha log t C1 of L bar divided by dimension raised to the dimension of y alpha plus log on norm integral on yc log of s C1 of L bar dimension of yc. Okay, so there is really two parts. By iterating the definition, there is the height of the codimension 2 cycle dvs dft plus a sum of two terms, this integral plus this integral. Proposition 2. IST is the same as ITS. So we get symmetry of infinity. C is the same as ITS. Again, I will prove this later. So the claims that we can conclude from that, because ds is equal to the Echelle bar of ds dt minus st, and I can exchange SNT here and SNT here. So if I do so, by the symmetry, I will get dt. That is, I could first put the divisor along y alpha, or start by applying the divisor along z beta. And the two constructions, according to this proposition, give the same thing. So ds is equal to dt, and this is enough to prove the theorem, because if I have two sections, S and S prime, there exists a section T such that the divisor of T does not meet, well, meets properly with the divisor of S, that is, there is no common component, and I could as well ask that the divisor of T has no common component with the divisor of S prime. This was a lemma where it was shown that there exists T, lemma 7, T in general position. So now I get ds equals dt equals ds prime. So this is what I wanted. I wanted to show that the right-hand side is the second part of the theorem, is independent of choices. And this gives that. So I think I will stop here.